To chair this session and introduce my former teacher from Vivekananda College, Professor R Vittal. We always admired his teaching, and he was considered to be one of the finest professors there. And he taught us probability and statistics. So I personally remember those classes. And subsequently, when he got associated with math science, he did his PhD here under the supervision of Professor Vasudevan. And he has continued to be very active in the field, giving lectures at various conferences in India. And I think he even came once to the University of Florida when we have had a special year in probability and analysis. So it's my pleasure to invite Professor Vittal to give his talk on stochastic dynamics and passage times for diffusion approximation. Professor Vittal.
To the organizers of this conference and Professor Krishna, I'm really grateful to him for inviting me to this conference to give a talk. We used to attend a large number of small seminars conducted by Professor Alladi Ramakrishnan when he was the director of the Institute of Mathematical Sciences. Right from 1970, I remember. And one of his talks, he told me that Kolmogor's forward equation and backward equation, they are different, but they lead to the same solution. I could not follow his talks thoroughly, but this ringed in my mind very clearly and focused me to think about this factor. That's why, even though I've done few other topics along with Professor Vasudevan with math science, I preferred to choose this topic, stochastic dynamics of first passage time and diffusion approximation. The idea is that when you consider the motion of a particle between minus L to plus L interval, and we want to study the first exit time. Since Professor Ramakrishnan told me that backward and forward equation lead to the same solution, but even though the equations are different. We tried with the forward equation, some complication came, and this idea struck to me, and about more than 12 papers we have published based on this idea. We will start with the elementary idea from the beginning that we are considering stochastic dynamics of the first passage time and diffusion approximation. See, several papers appeared on one-dimensional random walk models to study the first passage time with one or two barriers. Such problems find applications in spike train activity of neurons with excitatory and inhibitory impulses. In storage models, we are interested with process moving randomly upward and dynamic downward, but we are interested in the first emptiness period and also the first overall period of the dam. In queuing, we come across the busy period of the server. In insurance, we consider the ruin probability, and also when the risk reserve reaches a standard value, dividend has to be distributed to the stockholders. So large number of applications are there on this elementary idea of boundary value problems. See, Lindbergh and Schuller considered the discrete version of this random walk, and Weiss and Szabo in 1981 introduced the continuous version of this Lindbergh model. But they studied the first passage moment problem for a class of master equation with separable curve. Here I would like to point out the idea triggered into my mind because of Professor Alladi Ramakrishnan that the backward equation might lead to solution rather than the forward equation in a closed form. Because of the crossing of the barrier, to introduce the boundary conditions in which even Weiss and Szabo failed in their paper, I will point out, by virtue of the fact that Professor Ramakrishnan told us to study with the backward equation, For the crossing probabilities, we used Richard-Billman embedding technique to decide a continuous process jumps outside the interval minus L to plus L. What Weiss and Szabo did is that they omitted that because of the random jump, the first jump could be so high that the process could be crossed even in the first jump out of the barrier. Now, that is the Dirac delta function involved in such situation, and to incorporate that condition into the backward equation, we approach Richard-Billman technique of embedding. When you differentiate the process in order to obtain the moment, the term that they omitted by Weiss and Szabo has not affected them in finding out the moments of the distribution. Once you get the Laplace transform function or the Fourier transform function, to get the moments, we go the derivatives of this function, and as the last term of the jump which crosses the barrier is unaffected by the derivative, their moment fortunately work out nicely. So, we consider the first passage time outside the interval minus L to plus L using the embedding equation. There is 8 moments, we have gone to the first passage time problem. Weiss and Szabo considered jumps in the forward motion, jumps in the backward motion, both are random in nature. Even though we started to demonstrate that we can do little more than Weiss and Szabo, we have introduced linear drift into the process. We have introduced exponential decay into the process. This turned out the differential equation turned out to be complement hypergeometric function, and we were able to get the closed form solution to that. Ultimately, we found out that the embedding technique nicely worked out so well as long as the kernel is in separable form. So, when we gone from the exponential jumps of the transition density, we have gone to the gamma type and also general separable, in which we proceed to obtain the solution in a closed form, and the moments of such a solution similar to the Fokker-Planck's equation also that we have demonstrated. Now, see, the Liedenberg and Schuler model is a discrete version which is now given there, and Weiss and Szabo's is xt is the level of the process at time t, x is the initial level of the process, and sigma zn the jumps of size zn which are Poisson in nature in the forward direction, zn minus or jumps in the negative direction, both are Poisson in nature. Now, we define a function f of xt as the probability function of crossing the outside the interval minus L to plus L for the first time in a time interval t. Now, x of 0 equal to x naught, the initial positionary path. Now, arriving at the solution, we came across certain difficulties to arrive at the closed form solution, and thereby we decompose this f of xt in terms of f plus and f minus. F plus denote that the very first jump, initial jump is in the forward direction, and f minus denote the initial jump is in the backward direction. We write down separately the embedding equation for f plus and also f minus, converted them into the integral differential equation, and later by the process of differentiation we converted into the integral differential equation. The main theme of this work is how the initial condition, the boundary conditions are embedded into the process of the solution. Now, we write the solution for f dash xt. The right hand side comes to, there is no Poisson jump in the initial interval of backward motion, in the initial interval of time t, and there is a jump, and ax comma y is the transition density, and the first jump itself it has crosses the plus L part of the interval, and therefore we introduce the Dirac delta function there. When you take the transform to this Laplace transform mean, this converted into a differential equation, and the Laplace transform of the Dirac delta function turn out to be 1. Now comes the question, how are we going to handle with the kernel ax comma y? To handle the kernel ax comma y, first we simply started with the exponential jump. The transition takes x to y in the form of the exponential factor e to the power of minus lambda into x minus y. Now, that is going to enable us to convert this equation into a differential equation. Now, taking the transition density in the exponential form, feeding into the integral differential equation or the master equation that we have constructed, and then substituting the transition there, we now get a differential equation. When we try differentiate this with respect to x, this turned out to be an ordinary differential equation with constant coefficients. Now, similarly, f minus is the transition density where the first jump is in the negative direction. We are not interested in f plus or f minus alone, we are interested in f. Therefore, we consider the certain algebra to eliminate f plus and f minus and ultimately arrive at a differential equation in the process. Now, we see how simple a 11th standard student can understand the second order differential equation with a constant coefficient. Now, we write down the solution of this differential equation in this form, and see a, l and dl are functions of l, which are the extremities of the interval. We are interested in the crossing of either of these two barriers, and we treat these barriers initially as absorbing. Later we are going to consider one of them as reflecting or both of them will be reflecting. When you consider both of them reflecting with 0 and L as the barrier, automatically it corresponds to the case of the overflow of the dam and then reset at the top level, or the emptiness of the dam and reset at the lower level 0. Now, having got the differential equation, now I am interested in going how you determine A and B. The Richard-Bellman technique comes out in this form. We write down the total differential equation, which were originally it was difficult for us to solve in closed form, and now we have written down the integral differential equation for the entire process with L as a barrier and minus L as the barrier, and now we substitute the solution that you have already obtained into the integral differential equation. Since the ultimate solution is independent of the position of x, we have to see that the coefficient of e power m1x and e to the power of m2x should vanish separately, and thereby we arrive at two conditions. Solving these two conditions, we determine A and B, and hence resubstituting in the general solution that we have obtained, we get the complete solution in a little complicated form. Now, the f bar s is called in terms of the hyperbolic function. One can also test that now when you put t equal to infinity is equivalent to putting s equal to 0, and the ultimately Carlyle and Taylor condition that the total probability of exiting of the interval in infinite number of time should be equal to 1. Now, mean passage time is where Weiss and Szabo attempted, and they got successful even though there was an error in writing down the first passage time. They couldn't arrive at the first passage time solution, and therefore they shifted to the moments. Now, when you want to arrive at when we have the Laplace transform in closed form, the first passage time solution is now given by the nth derivative of the transform function, and it is possible to write down the differential equation for the nth moment. For the special case for n equal to 1, we can write down the solution as in Szabo I have written down. For me, it did not solve the differential equation. Since I know the solution closed form for f bar SL, I directly get by derivative the solution for that. This also, and further one other mistake that Weiss and Szabo did is that he considered the first passage time in separable form, fxt as f1x into g1t, which violated the condition that the ultimate crossing of the barrier is equal to 1. In general, this fxt cannot be expressed in separable form. Now, we go into the reflecting barrier. Before going into the reflecting barrier, I will speak about the kernel x comma y. In the solution that we have now gone into, I have taken conventional, the most simplest form, namely the exponential form. When you go into the Gamma type, how it is going to occur? When you go into a general separable form with the normalizing factor, how it is going to happen. When you take the boundaries as constant minus n and plus L, you make the one of the boundaries as time dependent, especially in business association. As time changes, the fixed reserve might also change. Therefore, the time dependent barrier is to be introduced. Richard Bellman technique works out nicely also when the barrier is time dependent. Many conditions are closely allowing us to proceed into the closed form solution with the embedding technique. But the other methods are also available. Each method has its own merits and demerits. When I take into Kielson's method of compensation technique, I will put in contrast why Richard Bellman technique enables us to get the solution in a closed form, but not the solution of the moment so easily using the Kielson technique of compensation function. Now, reflecting barrier. What it means, the reflecting barrier? When it crosses L, just like in the EKMs of a dam, when the process crosses the top of the dam, the water goes west and the level remains the same, and then the dynamics of the process continues and it might become empty or again once again crosses. So any number of crossing is allowed before first emptiness, or any number of emptiness is allowed before first overflow. All these situations could be defined so easily by use of the Richard Bellman's embedding technique. Now you see that, now when you consider the crossing of the barrier, what I now introduce is that look at the form that in the second term F1 minus LT. That means when the lower barrier is taking as a reflecting barrier, it has crossed that and it resettles at minus F. The F1 minus LCD is nothing to do with the integral equation, therefore it can be taken out. Since I know the solution for F1xt is A e power m1x plus B e power m2a, I can substitute and solve the two equations and slowly close that. The solution, we feed into the solution, we also solve the two equations and ultimately arrive at the solution in the arbitrary constant to be determined. The solution comes in a little complicated form, and it also satisfies all the conditions of the problem as explained in other standard textbooks. Now we go into the diffusion approximation. Large number of jumps are taking place. We make the size of the jump so small, that means we allowed lambda tending to infinity, and very large number of times the Poisson intensity is very high, mu tends to infinity. So mu tends to infinity, lambda, see 1 over lambda is the average size, therefore lambda tends to infinity, 1 over lambda tends to 0, size of the sum tends to very, very small, and proceed to the limit that at the second moment it turns out to be d, a diffusion constant. So when you proceed like that, we write down P plus and P minus in the general way, removing the barrier minus n and plus L, ultimately eliminate P plus and minus P minus. We arrive at the second order differential equation. We divide by, throw it by lambda square, proceed to the limit in the, as we explained with the statistical feature of the problem, and we arrive at the simple diffusion equation. We can also go into the diffusion approximations with exponential decay and arrive at this solution in Wiener form. Now, for this solution, we have the first passage time in a closed form and also the moments in closed form. All the moments can easily be arrived at since you know the first passage time. The various derivatives of the first passage transform at L equal to 0 gives the various moments of the system. Now, the moment that we have arrived at coincide with that of Weiss and Szabo, but Weiss and Szabo studied only to arrive at the moment, since he pointed out that the first passage for crossing the barrier, he eliminated, so that to say, he didn't say it is not possible, he eliminated in one of the papers appeared in 1981 Physica journal. We now take the generalized kernel. In the generalized kernel, I take my transition density Ax comma y as lambda power n plus 1 by 2n factorial into modulus x minus I whole to the power of n e to the power of minus lambda into x minus y. So this is going to be this 2nth order differential equation. When I have both way jumps, I get a second order differential equation. Now this is going to be, if I take n equal to 1, it is going to be a fourth order differential equation, and ultimately in general form, it is going to be differential equation of order 2n. Now we arrive at the same form for f plus and f minus. A little complicated algebra has to be done to arrive at the solution, and we finally landed in the fourth order differential equation. Now see, having seen the fourth order differential equation with constant coefficient, we can go into the general solution. Feeding this into the embedding technique, we can completely arrive at the solution form. All the moments can also be obtained. These moments also satisfy the condition of Weiss and Szabó, as our results show the same results as that of the Weiss and Szabó. Now we go into the separable kernel general form. Look at the transition density. We take the form Ax by rho x, where y greater than or equal to x, by Ax rho x when x greater than or equal to y, for forward jumps and backward jumps, and this in separable form. Separable form is one of the conditions in order to arrive at the closed form solution to this boundary value problem. So when we suitably incorporate into the f plus and the f minus, the differential equation turn out the Ax comes outside or By comes outside. Therefore, we can differentiate with respect to the initial position x, and hence arrive at the solution in a very nice form. Where what are A dash and B dash? A dash and B dash are nothing but the derivatives of A and B with respect to x. Now, this equation could easily be solved, and then we have a complicated form, and I put this equation in the form f plus, we get in terms of a integrating factor, separable form, and therefore we can solve it, arrive at the solution in this, which identify with that of the Fokker-Plotz equation. See, now the equation turn out to be, for the moments also we can go in, ultimately the moments turn out to be Fokker-Plotz equation of the type. Now, so far as the philosophy of the Richard-Bellman embedding technique is concerned, the incorporation of the boundary condition into the initial delta t, what Professor Ramakrishnan did, what is going to happen initial delta time analyzing the process is equivalent to what is happening the final interval of time and dt, and proceed to the limit. You see that the solution is the same even though the differential equations are different. Now, all these results we get up to the Fokker-Plotz type equation with reference to the backward technique. Now, since I mentioned that forward equation could also be applied as Professor Ramakrishnan's sayings, still remember I mind that in the old room at 12 to 1 used to give everyday lecture as soon as he come to the institute to the student, and I was attending his lecture, and Richard-Bellman's technique he used to point it out. Now, when we go into the forward equation, we apply Keelson's compensation function. What the Keelson's compensation function tells is how to convert a boundary value problem into a non-boundary value problem. So we have a boundary at x is equal to minus L and x is equal to plus L. Now we introduce a corresponding compensation function for the particle leaving out of the boundary, and the compensation function corresponds to the first jump of the process. The idea is that using the inversion theorem of complex function, one can easily find the solution in terms of the Green's function of the process. Very close form for the first passage time is obtained in terms of the Green's function of the process. Even though the solution by the embedding method, when the exponential decay is there, which turn out to be in terms of the hypergeometric functions of 1fn function type, here what will happen is that when you introduce the exponential decay, we converted by a suitable transformation into a linear decay problem. Once we converted the differential equation into a linear decay problem, it turned out to be a differential equation with constant coefficient, and therefore Green's function technique could be obtained to see what could be the solution and retransform in terms of the original exponential decay problem. But finding out the moments is not that easy because the Green's function turned out to be very complicated. But when we introduce the time-dependent barrier, when we study the neuronal spike start time, considering the potentials are during to inhibition and exhibition of the electrical impulses that occur in the membrane potential of a single neuron. It so happens that the first passage time is to be determined on the average passage time, and we have to introduce the refractive period, because after one firing it has to reset. Since there is an elementary interval of time between one firing to next firing, and we have to reset, mathematically we incorporate by introducing moving boundary problem. In the case of the moving boundary problem also, we were successful in introducing the solution by the method of Kielson's technique. We enjoyed both Kielson's technique as well as embedding method to put a one-to-one correspondence of the solutions for the moment, and also the closed form solution for the first passage time of the moment. Now, the generalization of this process to the separable kernel will lead into very complicated solutions of the first passage dynamics of the problem. We can introduce the Wiener type of problem also by introducing the exponential decay with the drift. In case of Green's function, drift could be equivalent to a non-drift problem by changing the transformation of the variable so that a Green's function of the drift process could be expressed in terms of the Green's function for a bounded process without drift. So these ideas have been put in my mind by Professor Ramakrishnan as a dedication to the Professor Ramakrishnan. Now I want to give a talk on this topic in this conference, even though we have attempted on some other topics too. Thank you very much for giving me an opportunity for this.
Thank you very much, Professor Vittal, for your very nice lecture. Any questions for our speaker? Okay, if there are no questions, let us give him another round of applause.
I told Krishna I am just crossing the age of his father now. Thank you very much.
So this is a book that was published in 2010, 2 years after my father passed away. So this is published by Springer Verlag. It's called The Legacy of Alladi Ramakrishnan in the Mathematical Sciences. And I co-edited this book with Professor C.R. Rao, the great statistician, and Professor John Clowder, a very famous physicist. Sudarshan and Clowder's book on optics is well known. Clowder was my colleague at the University of Florida until he retired recently. So we are three editors, because I dealt with the mathematics papers, Clowder dealt with the physics papers, and C.R. Rao dealt with the probability and statistics papers. And one of the nice features of this volume is not only there is a description of my father's life and work, the telegrams that were received for the math science inauguration are reprinted here. So that also makes it extra valuable. And one other point I'll make is Professor John Thomson, the great group theorist who was my colleague at the University of Florida, his last work, at least there, was on a certain matrix called the divisor matrix. And he dedicated that paper and put it in this volume. And when he got the Abel Prize, about which reference was made, in the Abel lecture he spoke about this divisor matrix. And that was in 2008. So I thanked Professor Thompson and said, this is wonderful for you to give such an important paper for this volume. And his answer was, your father deserves it. So that paper is also in this volume. I hope you enjoy it.